what I see is I have now narrowed down my constraints, and it's inside this triangle that's being limited by the brown line, the orange line, and the blue line. And actually the red line, even though it was part of the constraints, didn't really impact us at all. And there are a few points that I have to be aware of. So the first point that I have to be aware of, because what we talked about was that all of these regions have vertices that we're going to have to talk about later. One of them is right here where the orange and the blue line intersect. That's the coordinate 0, 0. This is a possibility of what we would talk about where it's the best use of their time. 0 hours for each. Makes no sense really, right? Another place that we could talk about is the intersection of the blue and the brown lines, and that would be at 45, 0, which means, of course, that if you're talking about that Mr. Chang gets 0 hours. Well, that doesn't really make any sense. That means they weren't sharing at all. So then our last place would be the intersection of the brown and the orange lines, which we're going to have to find later. But in this problem, really what we were supposed to do is just graph the feasible region. That was the instruction. So if you read back, it says graph the feasible region. So the feasible region is where all of these constraints are being held, which is in this region right here inside the green triangle. And so for right now, that's all we're going to do. This is the region that we're talking about inside this green triangle, the feasible region. The overlapping of all the different shadings. In number 2, a new shopping mall is being planned with 3 large stores and 80 smaller stores. We have to decide how many public parking spaces and how many employee parking spaces the parking lot will have. So as we talk about that, one of the things that I'm going to talk about right away is that my public parking spots. So I'm going to make X my public spots. And that was from one of the things that we were talking about inside of here, public parking spaces. I'm going to make my Y then the other stuff, which in this case was the employee parking. And that also was from the paragraph where they talk about employee parking. The first sentence that I read, or the first bullet, says there's room available to build no more than 2,500 spaces. What that tells me is that when I add these two things up, I can't exceed 2,500. Or in other words, my public parking and my employee parking together can be no more than 2,500 spaces. So this is the purple. In the very next line, they say they have to have a minimum of 2,000 parking spaces. So that tells me, which is kind of strange, I guess, to me, is that my X and my Y together, the total number of parking spaces, has to be bigger than or equal to 2,000. And then in the very next line, they talk about 4 times as many public parking spaces, at least 4 times as many public parking spaces as there are employee spaces. So the public spaces, X, has to be at least 4 times the employee spaces Y. And that came out of this statement right here. The last thing that I see is this last statement where they're talking about there has to be a minimum of 20 employee spaces for each magnet and 2 spaces for each smaller shop. So if I look at what that's saying, 20 employee spaces for each magnet means 20 times 3, which is 60 spaces for the magnets. And then 2 spots for each of the smaller stores times 8 is 160. So 60 and 160 is 220 parking spaces for the employees at least. So the employee spaces, which was Y, has to be bigger than or equal to 220 parking spaces. That's the minimum number of employee spots that they have to generate. So maybe I should say that on the video. So here we see a constraint where Y is bigger than or equal to 220. Normally we say greater than or equal to 0, but they already gave us some information, so I'm going to ignore the Y is greater than or equal to 0 now. And the last thing that I'm going to write down is the fact that I know that if I'm talking about the X's, which happens to be the public parking, I know that my public parking can't be negative parking spaces, so I'm going to write down X is greater than or equal to 0. And again, I didn't do that for the Y because they already gave me another minimum constraint. Okay, so in number 2, very similar to number 1, the first thing I'm going to do is I'm going to write down my graph. So I put down my coordinate axes. And I know that I have a total of 2,500 spaces, but I don't think that any of them are going to be, let's see, we had none of them being more than 2,500, I guess, so I can't go higher than 2,500. So I'll put 2,500 on one side and 2,500 on the other. And the X values were the public spaces. And then the Y values were the employee. And if I go up by maybe, I don't know, 500s. So here's 500, 1,000, 1,500, 2,000. And you'll be able to see this a lot better on your graph paper, I'm sure. 1, 2, 3, 4. So here's 2,000, 1,500, 1,000, and 500. And then I'm going to rewrite down the constraints so we can just see them. So if you look back to your purple constraint where you had the X plus Y was less than or equal to 2,500, what I'm going to do is I'm going to rewrite that as Y is less than or equal to 2,500 minus X. So all I did here was I moved the X to the right-hand side of the inequality by subtracting off X from both sides. If I graph that purple constraint, that means that I have a y-intercept of 2,500. I go down 1 over 1 for the slope, which means I intersect the x-axis at the same spot. So now my line looks something like this for that constraint. And it's a less than or equal to, which means I'm shading under that line, which basically means I'm shading this way. Less than or equal to. Our second constraint that we wrote down, which was in the orange, had that x plus y was greater than or equal to 2,000. Again, if I move the x over, what I will see is y is greater than or equal to 2,000 minus x. This means that my y-intercept is at 2,000. and my slope is -1, which means I go down 1, right 1, or I could go down 2,000, right 2,000, which would put me on the x-axis at 2,000. And these are parallel lines, actually. But in the orange case, I want to be greater than or equal to that, which means above the line. So now I'm shading in this direction. And what you can see is that our feasible region is now trapped between the orange and the purple lines. I'm going to go with the constraint that we talked about next. That was the kind of common sense constraint. The one that we said was in light blue, x is greater than or equal to 0, meaning that when we're talking about our public spaces, they have to be more than or equal to 0. If I were to draw that line, that's actually the same as the y-axis. And I want all of the values to be to the right of that because I'm greater than or equal to 0. In truth, this probably does not affect our feasible region whatsoever, but it shows that you understand that you can't have a negative amount of public parking spaces. So still, the overlap of the three colors is trapped between the orange and the purple lines. So you'll write down the constraint, you'll shade it, even though it really does not affect what we already know for the feasible region. And then we also talked about, they talked about the number of minimum parking spaces for the employees, and when we added all those up, that was 220. Or in other words, in our gray equation, we had that our employee parking spaces were more than or equal to 220. So that means you go to where 220 would be on your y-axis, and you draw a horizontal line all the way across in gray. And you want everything to be more than that in gray. So when I shade that in gray, that means I shade above that horizontal line. And this does affect our feasible region because now we're talking about, I know that I can't be below the gray line. And so we have some points that are already constraining us. So here's one intersection between orange and gray, one between purple and gray. And these are the minimum lower levels of where our feasible region will be. Okay, our last constraint was in pink, and we said that when we wrote down that original constraint in pink, that we had x was greater than or equal to 4y. If I were to divide both sides by the 4, I would see that my y is on the right with the symbol that looks like this. And if I divide by 4, that's the same as multiplying by a fourth. So I'd have 1/4 x on the other side because I divided both sides by 4. But I don't like to look at it that way. That kind of confuses me when the x is on the left. So I like to write it this way. Y less than or equal to 1/4 x. Or in other words, my slope is 1/4. I go up 1 for every 4 I go to the right. I go up 1 for every 4 I go to the right. Michaela, what's my y-intercept? In the pink. Nope.
I mean 1.
Nope.
0.
Yes. Good job. You can put a +0 if that helps you remember the y-intercept. So that means that my constraint in the pink intersects at the origin, and I go up 1 for every 4 I go across. So instead of thinking about it that way, if I were to go 2,000 to the right, how far would I have gone up? 500. Very good, Grant. 500. So 500, 2,000 is another point on this line. Up 500, right 2,000 is the same as going up 1 over 4, because 500 is 1/4 of 2,000. And I draw that line. And what I'm looking at is shading all of the stuff that is less than or equal to that line, which means that when I shade, I want to be below it. And our feasible region is the overlapping of all of those places. So what we're talking about is the region